We try to use natural archives to put more data points on the page that go further back in time so that we can better understand what the climate was doing even before the Industrial Revolution took off.
Good evening, everyone. Hi. My name's Gina. I'm the outreach coordinator at NOVA. Thank you so much for joining us tonight for our it's March, oh my goodness, Science Cafe. So I'm gonna be your host for most of this evening. So without further ado, I'm gonna pass it on to our speakers and enjoy.
Great, thank you so much, Gina, for giving us that introduction.
Yeah, thank you.
My name, again, as Gina said, my name is Christine, and tonight my partner in crime is Gabi Serrato Marks. We're both researchers from MIT and Woods Hole, and tonight we're really excited to talk to you all about what we do in the lab, our work to try to reconstruct past changes in Earth's history, particularly its climate, and what all those changes can tell us about what's going to happen in our future. So to start, I think I'm going to introduce, even though we're talking about things that happened thousands of years ago, I'd first like to put our research into context of what is happening today. So climate change is happening because of all the atmospheric CO2 that we are putting into the atmosphere. Our planet is certainly and surely warming. All of our models and our data suggest that this is going to happen and that average temperatures will continue to increase into our future. Even though this is happening, and scientists know that this is happening, we have less of an idea, or we're less certain about how precipitation changes are going to be redistributed around the planet. On an average, we do know that due to an intensified hydrological cycle as a result of more energy being in the atmosphere, we know that both precipitation and evaporation are going to have to increase on a global average. However, scientists are still trying to work out the details for where the precipitation is going to fall and where it isn't going to fall, mostly on a regional basis. Is more rainfall going to fall where there's already a lot of rainfall happening, for example, in places where floods are very common, or are places that are already dry going to continue getting even drier? Or is something different going to happen where actually some dry places are going to get wetter and vice versa? These are the kinds of details that scientists like me and Gabi are still trying to work out. And these are some of the biggest questions that we have for our future, because water availability is, of course, a very important part of humans' ability to sustain themselves. There are some indications that our hypothesis where places that are already dry might continue to get drier. There are some indications that in the United States that might be happening based on some of this data, comparing what's been happening over the last 10 or so years compared to what's been happening over the other parts of the century. And so from this map that we're showing behind me, you can see that a lot of the places in the Northeast, or even in the Sierra Nevadas in California, where we've been seeing record amounts of snowfall recently, those areas have been getting much more rainfall over the past decades than they have been in the other parts of this century. And so there are some indications that perhaps our hypotheses are being validated, but not all of our models and not all of our data confirm this. And so it would be really nice to get data on how much rain fell before this period of time. Again, during this period of time, we were already, building factories and emitting so much CO2 into the atmosphere. It would be really nice to understand how rainfall patterns were changing even before humans were having such a dramatic impact on our ecosystems and our climate. Our longest instrumental rainfall record actually is pretty close to home. It's in the Blue Hill Observatory, which is in Milton, Massachusetts.
How many people have been there? Okay, a few.
So they coined themselves that they're the home to the oldest climate record in the nation, which is pretty awesome. And so they've been collecting data since 1885, and I think the oldest records from the world aren't too much earlier than that. I think those only started in the early 17th century, 18th century. So what do we do if our earliest instrumental records of rain gauges collecting rainwater, what do we do if those only began 200 or so years ago? Well, that's where scientists like me and Gabi come in, where we try to use natural archives to put more data points on the page that go further back in time so that we can better understand what the climate was doing even before the Industrial Revolution took off. And so you could consider us climate detectives. We're looking for evidence of past climates on Earth in the landscapes to try to determine how precipitation patterns have changed throughout Earth's history. And so tonight, we're going to talk to you about just two kinds of natural archives that help us reconstruct these past precipitation patterns. I'll be covering ancient lakes, and Gabi will be talking about her work looking at ancient cave deposits and the stories that those have to tell. So I think I will now pass it on to you.
Thank you.
Yeah.
So some of you might be a little bit more familiar with tree rings and using those as past archives of climate change. This is a really similar approach. It's just with slightly older and sometimes, I think, more temperamental records. So we both work with a lot of different kind of questions and tools to help us work on these precipitation questions. So we look at time on a lot of time scales. I work in the past couple thousand years. Christine works on that time scale and much longer than that too. Mm-hmm. Millions?
Not yet millions.
Not yet millions.
No.
Almost to millions. Hundreds of thousands of years. I also work on timescales that are just a year long, so it's a wide range of time that we're looking at. We also are looking over changes in space that range from a few millimeters, so how big is this tufa, which is the rocks that are here, kind of how much did it grow per year. And then we're also looking at lakes or caves that span kilometers. So we work on these giant ranges of space also. And then we are going to show you a lot of pictures of us outside and doing our field work, but we actually spend most of our time like this in the lab, pipetting and using chemistry on our rocks to try to learn a little bit more about exactly what was happening a really long time ago. But to do that, as Christine said, we're still really learning about the climate now, and so we also use modern monitoring to address some of these questions. You can see here a map of all the regions in North America with karst. So those are sort of the basic ingredients to make a cave. That doesn't mean that there's caves in all of these orange and yellow areas, but there are caves in a lot of them. You can see a box kind of in the middle of Mexico there where there are no circles, and that is denoting that there are no cave records from that area. So even though there are all the ingredients for caves, scientists haven't yet established climate records from that region. So we went and are trying to do it. We haven't done it yet, but we're on our way. Part of the reason why there aren't that many climate records from this area is because they're hard to get to. This is me rappelling actually back up out of a cave, and that was a 30-meter drop downward. So I had to learn how to go up and down a rope just to get to this cave. So there's a lot of reasons why people haven't gotten records from this area, but one of them is just that the caves are really difficult to access. Even though you might think of most of Mexico as cacti and shrubs, a very dry place, there's actually a lot of parts of Mexico that are more like this. This is the northernmost cloud forest in the world. So this is in Tamaulipas, Mexico. And one of the questions we're trying to ask here is, this region, which is now really wet compared to its neighboring regions, was it always that wet? And the reason it matters is because we need to know if it's going to continue being wet in the next 50 or 100 years, or if people in this region need to start preparing for water scarcity. These are the three caves where I'm really working. They're all in that region of central Mexico in Tamaulipas and San Luis Potosí. Again, up in Cueva Bonita, up on the top right of that screen, you'll see that today it's a pretty wet region. There's plenty of rain. Whereas in Cueva de la Puente in San Luis Potosí, it's really dry, and it is that dry kind of cactus type look. So the problem is that in the past, we don't know exactly what that looked like. Here's again, really dry, really wet, trying to kind of hammer that home. Hopefully you're getting it. It's dry, it's wet, got it. This is going to show you a little bit of a background on how we go to get the stalagmites that you see. They're now on that chair, but we'll pass them around again. We go all the way up into a mountain, and then we have to rappel back down into the cave. So the cave entrance is actually at the top, not at the bottom. So this is us getting all geared up and ready to go down. That's Kevin, who goes to UC Irvine, so I guess that's their sign, so he had to do that. But we're rappelling all the way down and in. And this is a big team of people. There's at least 5 people every time we go caving, but we have to try as hard as we can to not disturb the cave environment, of course. We collect a lot of drip water. This is the second drip you see me collecting from. And then soon you'll see the third. And I think there's even a fourth, yep. So those are all the drips that we collected. We spend a lot of time standing under stalactites with a cup trying to get that modern monitoring data. It actually takes all day. So we hiked in the morning, and this is us hiking out of the cave at about 9 p.m. This is a close-up of what it looks like to collect water from a tiny stalactite. This is sort of a baby one, and we actually call them soda straws because they're hollow in the middle. And then here on the right, you'll see a drip counter. So every time one of those stalactites drips down, that small machine there collects basically a count. So it says, okay, that was 1 drip. And it does that for as long as the batteries will last, which is usually about a year. So this was taken in June of 2018, and we're going back in May of 2019, hoping that the batteries have not yet run out. It's difficult to make technology that will work well in caves, which are cold, wet, very wet sometimes. Sometimes the whole cave floods, and that they can store all the data until you go back, sometimes years later. So it's hard to get some of this data from way down at the bottom of the cave. This is an hour's hike from the entrance also. So it's not only a 45-minute hike up, it's then an hour hike back down, which is kind of hard to wrap your head around, but we're going sort of twists and turns, and it takes a long time. You can see that there's this really nice white crystal calcite, and if you haven't been in that many caves, you might think that's just how they all look, but we're actually really, really lucky that this is how they look. This is a really special, we call it a decorated cave. It means that it has plenty of stalagmites and stalactites. So we take samples, as few as we can, but they look kind of like this, where they have this white, slowly growing texture, and that's exactly what we want. But we also want to know what the stalagmite would look like if it was growing today. And so we place those glass plates down and make a fake stalagmite, sort of a human-generated stalagmite, leave that there for a few years, and when we go back, we get the stalagmite that formed from exactly the conditions that we know about. So we're monitoring it, and then we have this brand new stalagmite. So a lot of work goes into just kind of prepping for this study, which is part of why I'm saying we're on our way to having this data, but we don't have it yet. This is a stalagmite that I took from exactly that spot that I was showing before, where we have a drip counter and we're taking water samples. That's what's shown on the left here. And each of those horizontal lines is a sample that I, or the undergrads that I work with, have drilled from that stalagmite. So that's about 2 millimeters per sample. And that is what's going to become our climate record. Each of those will be a data point in sort of a spaghetti plot that shows, was it wet or was it dry? We also have to find out how old they are. So this stalagmite here that I'm showing is about 1,000 years old as 2,000 years old. And those vials that I'm holding are concentrated uranium and thorium, which is how we find out how old they are. Instead of radiocarbon that you might hear about for other archives, we do it all with this uranium and thorium dating. It goes back a little bit further. We can go back as far as 500,000, maybe 600,000 years if we push it. But mine aren't that old, which is good. I get lucky about that. Christine isn't so lucky. We take these archives, which are a range of different ages. So we have a tree ring there, a set of tree rings that goes back to 150 years before the present. That's what that BP notation is. Then we have that middle stalagmite, which is as old as 2,000 years old. And then we have this big, really old one from Cueva Bonita, which is the wet area that we're studying. And that goes back all the way to 26,000 years before present, which is before the last glacial maximum, or the Ice Age. You know, the Ice Age movie where everything's covered in ice? That was about 20 to 25,000 years ago. So this is even older than that. We've gotten to see exactly what this area went through when it changed from a glacial to the current landscape. There were never glaciers there in central Mexico, but the rest of the climate was experiencing that glacier. Does that make sense? That's sort of like a weird, okay, great. Getting some nods, I'll take that. With that slightly unsatisfying ending, Christine will tell us a little bit more about ancient lakes and how we can study long-term, big changes while I'm studying little millimeters of change in a stalagmite. Cool.
Great. Thank you so much, Gabi. I would love to go spelunking with you sometime.
Yeah, I want to go to your lake, so maybe we should just trade.
Yeah, you should invite me to go crawl and get my knees dirty and everything. That would be awesome. Okay, yes, so as Gabi said, I'm going to now take the reins and start talking to you all about what I've been doing studying ancient lakes. So I first like to start by talking about how I even got interested and introduced into this particular niche field. And I was actually first exposed to this from a field trip that I happened to go on as a freshman in college. And during this trip, we went to the western United States. It was the first time that I had ever seen mountains growing up in upstate New York. And I was blown away by all the things I saw, you know, desert sand dunes, mountains, as I already said. But another thing that I was blown away by was this really interesting history that I had no idea had happened in the western United States. So if you've ever been to this part of the country, you'll know that it's a pretty dry area. The Great Salt Lake is not really a lake anymore. It's pretty much salt. And there are many other valleys in this area that are also pretty arid. It turns out that between 30 and 10,000 years ago, that entire area that is now desert was actually filled with these enormous lakes. So here's a map behind me that shows that during this time, shows the locations of all of these enormous lakes. I'd like to point out in particular the one called Lake Bonneville, which is in Utah. This lake is very near and dear to my heart because I happened to work on it, but also it was the biggest lake that occupied this region between this really interesting period of time in Earth's history. It was, to give you some context, so it covers half the state of Utah, and so its surface area is very comparable to, I believe, modern-day Lake Michigan. And at its deepest, it reached approximately 350 meters. So it's a really enormous lake that existed during this time, but now the only remnant of it is the Great Salt Lake. So pretty interesting. Now, how do we actually know that all of these lakes existed if they no longer are there now? And so the first, well, maybe not the first person, but one well-known geologist went around. His name was G.K. Gilbert. They call him the father of modern geology, actually. And he happened to be roaming around on his horseback and noticed these interesting lines that were dotting or just kind of on the mountainsides, like stair steps. And he noticed, that's really interesting. I wonder what sorts of things made those stair steps in the mountainside. And he, along with this artist that was with him, sketched all these beautiful terraces that were in the mountainsides. And it turns out that these stair steps that are depicted in these sketches are actually ancient shoreline features left behind by, in this case, Lake Bonneville, when it was at the elevation of those plains that are depicted in this picture. I happened to be lucky enough to visit Lake Bonneville in 2012, so this is my photograph of perhaps a similar location to what was depicted in that sketch, where you can really see these lines along the mountainside. They're essentially stair steps or platforms that you can walk up almost. And so these features in the mountainsides are evidence of some body of water that used to exist at the elevation of those features. So that was my first exposure to this idea of ancient lakes existing. And I kept thinking about that for all my 4 years of undergrad and decided, oh, I definitely want to keep studying this for my PhD. And so for my dissertation at MIT, I've been looking at ancient lakes, but in the central Andes, which is another very dry place. Here behind me, you can see this map of modern-day rainfall, and the central Andes doesn't even get a color for rain because there's not that much rain that falls. So not much rain. It's one of the driest places on Earth today, and yet we see on the landscape evidence of, again, there being enormous lakes in this region. So behind me is a satellite image of one such lake, and if you can kind of make out those white arrows, those are pointing to, again, these ancient shoreline features that the lake, when it existed at that shoreline, they carved away at the debris and might have even deposited some of those bathtub-like rings that are shown in the middle top part of that image. So I was very lucky and I got to go to this place, and if you actually walk along this landscape here across those shorelines, what you can see on the ground are those, again, arcuate-like barriers. And in this image behind me, the highest shoreline in this basin is actually that horizontal line that's kind of darkened in the background and highlighted by the lack of snow. That's actually where the highest shoreline was when this lake was at its maximum extent. If you continue to walk around, sometimes, in addition to finding these interesting paleo shorelines, you can also see deposits of tufa, which I will gladly now pass around. These are actually you can think of these as fossilized remains of algae and other kinds of microbes that used to grow during the time when the lake actually existed at the elevation that these things were growing in. So I'll pass this around. Thank you.
Like this or like this?
Yeah, so that one in particular is really interesting because I'll show a picture later on. But this one was, I found it in this orientation with many other cones, which indicates that the morphology of the organism that helped to build this also wanted to have this kind of inverted cone shape, which is pretty fascinating. So I'll pass this around too. So this tufa that's now being passed around is all of the whitish beige looking stuff that's covering the landscape here. In the Andes, most of the rock is volcanic in origin, so it's made of basalt. It's very dark and purplish in color. So it's really, this kind of material that's white really stands out from that background rock. Here's another image showing the contrast between, again, this tufa that's just covering this whole entire landscape, contrasting that with the original bluish, purplish volcanic rock that's making the bedrock here in this region. And so again, here's another image just for good measure, showing that it's kind of coating the original rock. And actually, this is that photo of one of those inverted cones. There I am, trying to block myself from the high winds that occur in the high altitude central Andes, while also taking notes.
Is it a desert?
Yeah, so it's extremely dry. Obviously, There's no water there.
But it's cold.
Anymore. But it's also cold, right? So we are working at around 14,000 feet in elevation, so also not that much oxygen up there. So the first few days I was definitely gulping like a fish, but managed to get over it after a while. All right, so for these ancient lakes, the key idea that I wanted to apply here was that since we know that those paleo shorelines indicate that there was a lake at those elevations at some point in time, it would be really lovely to know when those lakes existed. When did the lakes that made those paleo shorelines, that carved those terraces, when did they exist? And if we could determine when they existed, we might be able to build a record of the competing balance of precipitation versus evaporation. These lakes that I study are very special in that they are landlocked. We call them the closed basin lakes because there are no rivers or streams that then redirect the water into the ocean. And so you can think of them as essentially Earth's natural rain gauges, where any precipitation that falls within the basin can only leave through evaporation. And so if we can figure out when those lake levels changed and how they changed, we're essentially getting like an ancient rain gauge record that goes back in time. And so the key point of how we determine when the lakes existed is by trying to figure out when these algae and microbes were last alive, when they existed to then form into these beautiful fossils that we are now, that I'm now lucky enough to collect and then bring back to the lab. And so that is what we do at MIT. We bring these samples back into the lab after we've recorded their exact location using a fancy differential GPS. I'm sorry, I'll backtrack a little bit. This is a video of that fieldwork, some of the fieldwork that I do. So we drive up the west side of the Andes, visit our sites, do a lot of hiking, and when we do come across a tufa deposit, I take out my rock hammer and try to chisel out a tiny piece of it. And those are the pieces that you are now holding over there. So they've come a very long way to now be in this lab at MIT. So anyway, when they do arrive at MIT, I take them into the lab. Well, first I cut them open and take a little bit of powder from them so I can isolate the uranium and thorium isotopes that Gabi was talking about for her stalagmite samples. Again, as she said, measuring the relative ratios of these isotopes tells us how much time has elapsed since those elements were locked into stone. And so that's how we tell time. This field work hasn't always been super smooth. The biggest problem that I've had is getting my truck stuck in a ton of sand. And so this is a cautionary tale for avoiding sand traps while you're out driving in the Central Andes. It can take a long time to dig yourself out. Even despite the problems, this is a really beautiful location, and I've really enjoyed my time getting to think about these ancient lakes and what they can tell us about our future. And so I'd like to end by just giving a short overview about the work, putting my work in the context of all the other work that hundreds of other scientists who also study ancient lakes, what all of our data says when we put it all together. Because again, there's no scientist that works, alone. It's always a collaborative effort, and we always try to, if we're good scientists, we always try to share our data so that we can get a global picture of what's going to happen. And so this map behind me is showing every point represents an ancient lake, and the colors represent whether the lake levels are high, medium, or low, where low is yellow in color, and high is dark blue in color, and medium is light blue in color. And so what I'm plotting here, you can kind of see in the sub-Saharan African region, all of the lakes are low because today it's a desert. And so are many places within the interior of Asia, for example. So it makes sense where the lakes are low today. But if we combine our data and we look at what lakes were doing 6,000 years ago, we get a completely different story, right? 6,000 years ago, instead of Africa being a complete desert, instead we have this vibrant ecosystem supported by all of these lakes, which is really interesting. And if we go back even farther, 21,000 years ago, there's less data because it's harder to find sites or ancient lakes that are this old. But I would like to point your eye to the western United States here, where before all of those lakes were plotted as yellow in color, very low, but now during this period of time, around the ice age that Gabi mentioned before, all of these lakes were much bigger. So those, again, are the lakes that I referenced in the very beginning of my spiel. So this is the kind of powerful information that we can come up with when all of us scientists bring our data together and to see how rainfall patterns have changed throughout time. And so I think we've been talking a little bit too much, so we would love to hear from you now. I think it's probably good to start with any questions that you have. Thank you for listening.
Yeah, let's give them a round of applause before we go.
For you.
So if you have a question, raise your hand and I will pass you the microphone.
Hi. So I have a question for Christine.
Sure.
When looking at the change in climate over the course of the last 26,000 years, how do you take into account the retreating glaciers in the models that you're creating for looking forward? How much weight do you give to that data?
Sure, yeah. That's a good question. So whether or not there is ice or not in the landscape is something that we call a boundary condition. So those maps that I showed, actually I can flip back. We actually use these maps as answer keys almost for our models, where we say, okay, we know from our hard work and getting really dirty out there and collecting all these samples, we know from all of that hard work that lakes in sub-Saharan Africa were much higher 6,000 years ago. And then we actually use the same models that we are using to project into the future to then ask, can these same models reproduce the same pattern that we see from all of these records? And during that time, when we do that, we make sure to remove or add ice sheets during this time, because of course those conditions were different, and so for runs that use this data as an answer key, we definitely put the ice sheet there as we know it. But then for models for today, obviously there's no giant ice sheet there anymore, and so we make sure that for modern runs we don't put that in there. But putting the ice sheet there will help us figure out how much of these patterns were a result of the ice sheet being there versus not. And that'll help us tease apart things that are happening solely because of man-made climate change versus natural variability. Does that answer your question?
I think so, yeah.
Okay, thank you.
Have you guys layered on the work that both of you are doing together and analyze the work then? Or there are, I'm sure, other ways of measuring exactly what you're measuring and layered on top of each other and seen what the results are?
Yeah, that's a good question. How should I even start? That's that's the big question, right? Is do the records agree? If you took a stalagmite from central Mexico, from a cave that's 1 kilometer away from another cave, do they agree? That's the question about getting your papers published, about sharing all of this, and it all gets peer reviewed, right? So other scientists have to read through what we say and basically say, yeah, that could happen, or no, I think your results are too weak and that's fake. So yes, I would say Christine and I haven't actually layered them on top in terms of doing central Mexico and central Andes stuff, but maybe we should. Our offices are only 2 doors down, so we should do more of that. But usually what people do is compare kind of apples to apples. So at least for me, I'll compare stalagmite records to other stalagmite records. So I'll say, I look a lot at the Yucatan Peninsula. There's a lot of really beautiful caves there. And then I look at some that are from the desert southwest in the US, because again, it used to be wet there and there used to be caves. And in general, what we're seeing is that, for example, 5,000 years ago, overall in Central America and North America, it was a lot wetter then than it is today. So that's sort of an example of an overall finding. And I can do the same thing that Christine's plotted here with lakes, except with stalagmites. Same thing with tree cores or lake sediment cores, that kind of thing.
Yeah, I'll add to that question, too. There have been more recently these large international collaborations where people have definitely started to try to compare. So apples to apples comparisons are hard in and of itself, but because of the pressing issues of today, we've been wanting to try to do more and start comparing apples to oranges, to compare stalagmite records with lake records and also tree rings and whatnot. And in those cases, sometimes, while they're very hard, there's a lot of nuances and details to consider when you do that. They have been pretty valuable in filling in the disadvantages of one kind of record versus the advantages of another record. For example, Gabi's stalagmites, very beautiful layers, sometimes annual layers, right? She can give us a continuous record of what's happening through time, but maybe only snap certain intervals of time.
It's a window.
Yeah. For my records are only snapshots in time. I can only tell you exactly what happened at one period of time. It's just a photograph rather than a running video, so to speak. But the advantage of my lake studies is that we can get a more quantitative idea of how much rain fell because we can reconstruct the volume and lake area and use them almost like a rain gauge. And so combining different kinds of records can be very powerful, but it is very difficult to do. But it's something that a lot of us scientists are definitely thinking about more and more, especially when we have mountains of data to sift through now.
How can you tell when the lake levels are higher than they used to be? So like in your example, they were higher than they are now, but is there a way to tell if they are higher than they used to be?
Like if there are sunken undersea bathtub rings.
Yeah.
Like if the lake level now is higher.
Oh, right.
What happens if they're underwater?
That's a good question. I think all of the places that I have visited, it's pretty dry today, and so I don't have to deal with the problem of, what if there's a shoreline underneath, interestingly. But that is a problem, for example, for people who study shorelines, reconstructions for marine terraces or sea level. Sea level has changed much more, and so you can get marine terraces that are enormous. They are
made
buried
of coral.
underwater. Yeah, and those can be seen if you have a good map of what's happening under the water. So I guess for your question, for the lakes that I study, it just happens to be that they're all dried up anyway, and so all of the shorelines that are exposed are the ones that are exposed. And another detail to add would be that because the climate has been dry, that's also probably why those shorelines are really well preserved for someone like me to then come and investigate. Because if it wasn't an environment where it continued to rain after those lakes disappeared, those features would probably all be eroded away or covered in vegetation. And so that's probably another reason why there's a bias towards me working just in deserts, because those are the places where these ancient shorelines are best preserved.
There are some caves that are underwater, and the stalagmites people have to go scuba dive to get the stalagmites, so that does also happen.
Can you two tell us about your least favorite and most favorite things about your field research?
One of my most favorite things about my field research is going to Mexico. My mom's family is from Mexico, so I really enjoy spending time there. I like going and having research that's connected to a place that I have a personal connection with also. I really like the food also, so that helps. And I like working in a team. I think a lot of the times we get sort of stuck in our lab work, and I do all my lab work basically alone, but when I'm there for days or weeks at a time with a lot of friends and having a lot of fun in the cave, I really enjoy that. My least favorite thing, honestly, is getting really, really muddy and dirty. It's like not really the appropriate answer for a geologist. I think we're supposed to be like very rugged, but I really hate dealing with the scent of the mud and bat guano, which is very difficult to get out of your clothes and your hair and everything after you've been in the cave for a few hours. So I always say that cave clothes never smell the same again. That's my least favorite part.
Awesome. Luckily, I do not have to deal with bat guano or anything like that. I'll start with my least favorite thing. I suppose, so I really disliked in the Central Andes the amount of wind that was there. Because we're at such high altitudes, we're basically sampling the middle troposphere of the atmosphere, and so it was just a constant barrage of wind, and I couldn't talk to anybody. No one could hear each other, and so in certain places that was the case where essentially because it was also sandy, I was getting kind of sand blasted as well, and so those days were not exactly the best. But luckily, those didn't really happen that often, and I was struggling to think about what was my least favorite part of fieldwork, because that only happened for a couple of days. I have far greater number of things to say about my most favorite things about fieldwork. They're kind of similar to Gabi's in that the teamwork, working with the team to essentially find these ancient shorelines, find tufa deposits. It's a really fun experience and pretty empowering for me, I think, being able to direct the science that's happening day to day. And oftentimes, I really enjoy the simple adventure of it. You don't really know what you're going to find, and you kind of have to plan as you go. For example, I was trying to be very meticulous with my fieldwork planning, and I said, okay, in order to get to this lake, I got to follow this dirt road from this satellite image. And so we drive many hours to get to this dirt road because it's this lake that's really remote that I really want to get to because not many people have been there before. And when we pull up to this road, it turns out to be this roaring stream that is definitely not a road, and it's just like this creek that's super active. And you might call me crazy. We actually just decided to drive up that stream to get to the lake. After much discussion, we had 2 trucks, so if one truck broke down, we could all at least try to make sure that the other truck was functional to bring us back.
Was your initial vote to do it or to not do it?
My initial vote was to do it, and I was with a bunch of other, perhaps like-minded folks, and so it wasn't a very difficult argument to make. Okay. But we made it to this lake after several sketchy stream crossings, but it all worked out, and we got to this lake, and it was amazing. It's actually one of these photos that I have here, actually. This one, yeah.
Is this the same lake, the top and the bottom picture?
Oh yeah, it is the same lake from different angles. Yeah, this lake is actually pretty interesting because during the morning when there's no wind, the water looks very clear and pristine. But then as soon as the afternoon winds kick in, they stir up all of this salt that's on the bottom of the lake, and it creates this opaque aqua green color that's very deep. And it was just incredible to see that change in color in just a span of 24 hours in this basin. So little surprises like this, after some interesting decisions being made, are all about what I love about fieldwork.
In the field of environmental science and climate change, I know your disciplines are really specific, and what you do is really down to your field. Are there other specific disciplines whose data has inspired you to go one direction or another, or do you think there are really specific disciplines whose data, in coupling with yours, would really bring significant conclusions?
Great question.
Yeah, you go first.
Okay. Yeah, so it's pretty interesting. I guess if I'm speaking as an individual now, not necessarily as a scientist, I do find it concerning that climate scientists have been saying for a very long time, climate change is happening, we have a problem, we should really try to do everything in our power to address it. And that conversation has been happening literally longer than my own lifetime, and yet we haven't really seen that much effort or advancements from the powers that be. And for me, that makes me incredibly sad that even though I'm doing all of this work and telling, providing more to the scientific community, more information about what has happened in the past, I worry that it might not make a difference in time for, preventing the worst kinds of impacts that climate change is going to have on humanity. And so recently I've been thinking more about carbon capture technologies. How do we draw down or remove the CO2 from the atmosphere so that we can eventually move to a zero emission society? I wish I could continue doing all this because it's what I love to do, but more and more I'm worried about whether, if I can keep doing that, when maybe I could also be doing something to maybe address the problem directly. Yeah.
It's hard to follow that.
Sorry.
Because I work on timescales that are really relevant for humans, and there were people that were living near the caves that I work in at the times that I'm studying them. I try to learn from archaeology and anthropology a little bit, and I think we've made some of the same mistakes where there's a history of sort of taking artifacts or taking stalagmites that our field didn't necessarily have the permission to take or the right to take. And so I think both the geology field and the archaeology, anthropology field are sort of navigating that now and shifting toward a collaborative approach and not taking more samples than we need. For example, we take as few stalagmites as we can because we want to preserve the cave, for example. So I think we can do more work together in terms of both how we do our research and our actual results of the research. Like, I would love to spend more time talking with archaeologists about what kind of research they have and what oral histories already exist about climate change in the Northeast Mexican region. Also, big data, I know is like the thing to say, but I do think that for both of our specific fields, just having really powerful computational tools is going to make a big difference in the future. And there's people in geology and earth science who do specialize in that, and so it's really cool to see what they're coming up with and what they're doing.
Yeah, if there's anybody in this crowd that wants to eventually study these sorts of things, having any kind of computational background is super valuable and highly sought after. So if you haven't taken a computer programming class already, definitely take it. It's given me so many interesting tools to use, and it's going to be very powerful now and into the future.
Yeah. We don't just dig with rocks. Well, we mostly do. We mostly hang out with rocks, but geologists can do computers too.
All right, let's give our presenters one more round of applause. Thank you. Thank you so much.
Thank you for coming.
Do you guys want to flip to your Twitter stuff?
Oh, yeah.
If you're interested in learning more about Gabi and Christine's work, you can follow them on Twitter and see what they're up to. And have a good night. Thanks for coming.
Thank you.
Thank you, guys.